To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. In Part B, the differentiation behavior of the capacitor under an input voltage V is discussed. Consider input current I to a capacitor. The voltage is an integration. Let input current I be the sum of a DC component and AC component. Then the DC term cumulates versus time. This is the accumulation of charge on the capacitor that we have seen previously. Taking the time average, it becomes the DC term again, plus the time average of the AC current integration. By the very definition, the long-term average of the AC integration is to vanish, leaving only the DC component. Hence, integration is the reverse of differentiation. Differentiation blocks the DC, let through the AC. Integration is to smooth out the cumulative AC component to zero, and keep only the DC. This is the same concept as averaging the measurements of something that fluctuates. We take the mean of the fluctuating quantity to get rid of the variation, or the AC noise, in order to get the mean, which is the true value of the quantity of interest. Consider the AC current be a pure harmonic with frequency omega also. Then the integration is also a harmonic but with an amplitude that is 1 over frequency. This terms means that the higher the frequency, the lower is the output amplitude. Again, this is exactly the reverse of differentiation on the left. Hence, integration also acts like a frequency-dependent impedance. It lets through low frequency, and blocks high frequency. Both of these behaviors are quite fundamental to the capacitor, and they are the reason why the capacitor is so useful. These functions are the building blocks, or the basic tool sets that one can use to construct circuits for controls and signal processings. Op-amp transimpedance amplifiers can be used to perform capacitive differentiation or integration. The transimpedance amplifier for differentiation on the left side is discussed in Part B. For integration, as shown, input voltage Vin is coupled to the input resistor R1, resulting in input current In at node A of the inverting terminal. The op-amp output, via the feedback capacitor, generates feedback current IFB, which is proportional to the derivative of Vout. Applying Kirchhoff's current law at node A leads to the relationship of Vout being linearly proportional to the integration of V input. This is an integrator or a low-pass filter. The circuit default design is for 0 dB gain at 0.5 kHz. It should allow familiar experimental demonstration from few hundred Hz to few kilohertz. Hence, one should look at the Bode plot while choosing the various resistors and capacitor. Observe how the Bode curve changes as a function of the component values. Try to keep it close to the default design. The idea is that while there is a bit of latitude in choosing the components, for the sake of uniformity in the class work, choose components such that the Bode plot does not deviate too much from the default. The point is to demonstrate the low-pass behavior, that is, signal decreasing from few hundred Hz to several kilohertz while still within a measurable range for the oscilloscope, that is few volts to at least over 10 mV. Use the app to calculate before deciding what to use for the circuit. Once the components are chosen, the circuit can be built. It is quite trivial to replace components if the circuit doesn't perform within a desired range, but it saves time if the first choice is adequate and the experiments can be finished in one try. This is an example of a differentiator, high-pass filter circuit, and an integrator, low-pass filter circuit. They don't have exactly the layout as in the wiring app software. Here, the plus 12 volt and minus 12 volt supplies are on two separated outer rails, and the ground are on the two inner rails. For use with the DG-lent AD2, the waveGen signal 1 and signal 2 can be used as the inputs to the differentiator or integrator, respectively, or vice versa. Both scope channels are used to monitor the input and output of each circuit. Given only two channels, only one circuit can be measured at a time. The 6-pin connectors have wires connected to both input and output of the circuits, and the scope input cables can be mechanically multiplexed to appropriate pins as needed. The tasks from C2 to C5 are quite similar to tasks B2 to B5 of Part B. However, C2 and C3 require some special consideration that has never been done previously, and this is discussed next. This graphic shows the schematic of the basic integrator circuit in the wiring app software. V-in is from a channel of AD2 waveGen. V-out is to be measured with AD2 scope channel 2. However, this circuit is not exactly an optimal configuration for certain experiments. Consider measurements of task C1 and C2. The input is a square wave, the output is an integration of a square wave, which is a triangle wave. In an earlier discussion, the input was decomposed as a sum of two terms, a DC component and an AC component. The DC component accumulates versus time, hence if it is not zero, it will contribute as a linear slope in the output. The slope is upward or downward depending of whether IDC is positive or negative. Clearly, this is highly undesirable for the measurement. In principle, with zero offset, the AD2 waveGen signal output should have zero DC component. However, random drifts on the millivolt or sub-millivolt level may occur, and although that can be controlled with a small offset, even slow drift can be a nuisance for data acquisition. The problem is random in nature, reports from the users in the past varied. Some AD2 were stable, some were not. The followings are some approaches to solve the problem. One approach that is directly relevant to what we just learned in this lab is to use a capacitor to block unwanted DC component from the AD2 waveGen as shown. The combination of a capacitor and a resistor as shown is known as first-order RC high-pass filter, which lets through high frequencies, blocks DC and low frequency. Since the measurements involve low frequencies, this requires a large non-electrolytic capacitor on the order of few microfarad or more. Such capacitors are not included in your kit. The resistor can be few hundred kilo-ohm. A potential pitfall to avoid is that scope channel 1 should be at the input of the circuit, which is at the node as shown, that is after the capacitor, not before it, which is connected to waveGen input signal. If you see a waveform that substantially deviates from the square waveform as shown, it means the RC time constant is not large enough at the frequency studied. Given that input shape, the output will not be triangle waveform as expected. Another approach is to use the RC filter on the output as shown, in order to remove the slow drift DC component of the integrator. Scope channel 2 can be moved back and forth between the two locations to ensure that the AC output signal after the capacitor is essentially the same as at the op-amp output terminal. We wish to remove only the DC component, with minimal distortion of the AC component. This photograph illustrates the RC circuit discussed above. A set of 3 capacitors are added together for 0.23 microfarad. The input impedance of the AD2 scope is likely in the megaohm range, and it appeared that 0.23 microfarad is adequate for task C2 and C3. The wire connected to scope channel 2 could be moved back and forth as shown in the video to ensure no observable distortion of the AC output of the integrator, while the DC drift component was removed. In a test at a frequency as low as 10 Hz, although electrolytic type is less desirable than the thin film or ceramic type, a 1 microfarad was found to work quite well in removing the DC drift while allowing the AC component passing through indistinguishably intact. This video shows the result of square wave input test. It is meant to be a self-standing video. For the sake of self-containment, the use of AC output coupling is explained. The experiment was arranged such that the output waveform before and after the capacitors could be checked. The objective was to observe for any waveform distortion of the integrator AC component as a result of the capacitive coupling. A symmetric square wave was generated, shown as the yellow scope trace. The integrator output is represented by the scope blue trace. The non-vanishing DC component could be roughly estimated by comparing the AC coupled output versus the direct output by moving the scope green wire back and forth as shown in the lower right inset. The experiment was set up to start at the lowest frequency range of interest. As shown, this was around 26 Hz or so. Then the frequency was slowly swept upward. As the frequency increased, the amplitude of the output triangle wave decreased as expected, but maintaining the slopes, as it should be. Here, the decrease of the amplitude could be thought of as due to shorter integration time, because the smaller period. Note the occasional clippings of the triangle tops. This was due to the DC drift becoming too large, causing op-amp output saturation. Adjust the offset can reduce the DC drift. By others' reports, this problem varied from setup to setup, from insignificant to mildly nuisance. Here, an offset of 2.85 mV appeared to help. To measure and report the output amplitude versus frequency, the scope time and amplitude scales were occasionally adjusted. When the signal amplitude approaches the noise range, persistence can be used for statistical average and get an accurate amplitude measurement. Eventually, the highest test frequency was reached, 10 kHz. Save your data for the report. This task uses the integration circuit as a capacitive transimpedance amplifier to integrate the photocurrent signal from a photodiode, like a pixel in a camera. However, there is a bit of extra work to use the photodiode in Lab 4, hence this task is reduced to just a simulation. The AD2 waveGen signal will simulate the input. The relationship of the output versus the input signal amplitude will be studied. The input signal is formatted for 75% duty cycle, with an offset such that the net integration is 0. Frequency is 30 frames per second, starting amplitude 200 mV. The peak-to-peak output is 7.06 volt. The input amplitude is 150 mV. The output signal is 5.24 volt. The input amplitude is 100 mV. The output signal is 3.57 volt. The input amplitude is 50 mV. The output is 1.77 volt. When the DC level caused signal distortion, the offset was adjusted to avoid the error. It takes time for the adjustment to stabilize. Lastly, input amplitude is 25 mV. The output is 0.86 volt. The output is plotted versus the input. The relationship is clearly linear. This is how a camera pixel works. The experiment was set up such that data can be acquired over the range of frequency of interest. Although the data will be analyzed with a computation app, appropriate measurement functions were set up to monitor the experiment and ensure its validity, especially the phase, for sanity check. The input signal amplitude was chosen such that the output amplitude is within the measuring range of the AD2 scope. Prior to the scan, the output indicated a high DC level, causing the output signal being intermittently saturated. Adjusting the offset helped solving this problem, which was important as the data would not have been valid otherwise. The frequency was scanned from 20 Hz to 10 kHz, and the signal was monitored for any potential problem. As the frequency was varied, the output amplitude also varied significantly. Adjusting both time and amplitude scales allowed the signal be inspected to ensure nothing unusual affecting its validity. Once the system was deemed ready, data acquisition was performed at selected frequencies for the frequency response measurement. The data were saved in CSV format for later processing. The data files are to be imported into this app for the calculation of frequency response. The output are two files. One contains the Bode plots, Nyquist 2D and 3D plots. Also a table of the signal parameters. The second file contains the record of the calculation. It is useful to inspect the record to detect if there are anything unusual. The experimental data can be compared with the theoretical model. For the frequency response, the experimental data, represented by the points and the lines connecting them, and the theoretical model, represented by the dashed curves, are in good agreement. Perhaps one note worth mention is about checking the phase. For the differentiator circuit, the output is a derivative, which should be a quarter cycle, or half pi lagging behind. But because of the op-amp negative sign, it becomes a half pi leading. Likewise for the integrator, which is a half pi lagging. These phase relationships are valid over a wide frequency range as shown in the data, and deviate only for the extreme ends where the op-amp finite bandwidth has effects. Thus, erroneous measurements, including connecting the scope leads to wrong nodes, or parasitic capacitive coupling effects can be caught early if these basic features are used for sanity check. For this task C5, it is sufficient to test a number of waveforms as shown in the demonstration, and capture the screenshot for each. This is the end of Part C.